LLM Training Stability, Residuals and Norms. In 2015, a network with 56 layers learned worse than a network with 20 on training data. Not a bug, a fundamental mathematical barrier that blocked AI for a quarter century. Today I'll show you how two techniques, residual connections and normalization, made it possible to build a skyscraper with 1,000 floors. One of them may turn out to be unnecessary. This episode is the story of building a skyscraper that won't collapse. We start at the moment when the building fell. The 56-layer paradox. Kai-Ming He and his team at Microsoft Research ran an experiment whose results seemed absurd. A deeper network learned worse than a shallower one, not on test data, on training data. The model couldn't handle even the data it was learning from. This wasn't overfitting. It was a fundamental inability to optimize. The source of this barrier was identified by Sepp Hochreiter in 1991. He wrote his thesis in German at the Technical University of Munich. The world didn't read it. 3 years later, Yoshua Bengio formally confirmed the same thesis in an English-language publication. The problem was fundamental. Gradients in deep networks vanish exponentially with the number of layers. The derivative of the sigmoid function reaches a maximum of 0.25. Each layer attenuates the signal by that same factor. After 5 layers, the gradient drops to the order of 10 to the power of negative 3. After 10, to 10 to the power of negative 6. After 20 layers, 10 to the power of negative 13. It practically disappears. Early layers receive no information about how they should learn. The analogy is simple: a skyscraper without an elevator. A message from the 55th floor has to pass through every staircase. After 20 floors, it's so faint that nobody hears it. Y19 with 19 layers was the tallest building of that era. The vanishing gradient problem blocked deep learning for nearly a quarter century, from 1991 to 2015. A network of 19 layers was the ceiling of capability. The path to 152 layers required a fundamentally new approach. The answer turned out to be brutally simple. The gradient highway, he and his team changed the approach. Instead of forcing each layer to learn the full transformation, they let it learn only the deviation from the identity. Output equals f of x plus x. The layer learns only the correction, the residual. The gradient of that expression is 1 plus the derivative of f of x. That component 1 from the residual connection guarantees the gradient never vanishes to 0. Even if the derivative of f is close to 0, the gradient signal flows directly through the skip connection highway. This is the elevator in the skyscraper. The message from the roof reaches the ground floor directly. It doesn't have to pass through every floor. The result was spectacular. ResNet won the ImageNet challenge in 2015 with a top 5 error of 3.57%, at a depth of 152 layers, 8 times deeper than VGG. A few months earlier, Srivastava, Greff, and Schmidt-Huber had presented highway networks with gated skip connections. ResNet won with the simpler version. No gates, pure addition. Simplicity beat complexity. The story didn't end at 152 layers. In 2022, Microsoft went further. DeepNorm made it possible to train a transformer with 1,000 layers. A model with 3.2 billion parameters beat a model with 12 billion, by 5 BLEU points on a translation benchmark. Deeper means better, as long as you have an elevator. The elevator solved transport. Air conditioning remained. Without temperature control of activations, a 100-story skyscraper still won't stand. Skyscraper air conditioning. Batch normalization revolutionized CNN training in 2015. 14 times fewer training steps on ImageNet. For transformers, it turned out to be fundamentally unsuitable. 4 reasons. Sequences have variable lengths. Models require small batch sizes. Running statistics don't fit new data distributions. In autoregressive generation, the batch dimension doesn't exist. The model processes one token at a time. BatchNorm regulates temperature based on the average across all buildings in the neighborhood. Absurd in a building with a variable number of floors. Layer normalization solved these problems. It normalizes per sample across the hidden dimension, independent of batch size, identical in training and inference, compatible with variable sequence lengths. LayerNorm measures temperature inside the room itself. It always works. For 5 years, LayerNorm was the unquestioned standard. The original explanation of its effectiveness, reducing so-called internal covariate shift, turned out to be wrong. Santurkar and collaborators in 2018 demonstrated that the real mechanism is smoothing the optimization landscape. LayerNorm doesn't maintain activation temperature. It levels the floor the optimizer walks on. This discovery will be critical in a moment. In 2019, the question arose whether subtracting the mean is even necessary. The answer surprised everyone. Less means faster. Zhang and Senrik asked a simple question and got a simple answer. RMSNorm keeps only the scaling by the root mean square. No centering, no beta parameter, just gamma. The result is clear. RMSNorm is 7 to 64% faster than LayerNorm. No published study has demonstrated significant degradation in model quality. Normalization operations are memory bandwidth bound, not compute bound. Every reduction in data transfers between HBM and SRAM memory translates to real savings in training that costs millions of dollars. Why the mean is unnecessary? Research by Gupta and collaborators from 2024 provided the proof. Models with RMSNorm spontaneously learn representations orthogonal to the uniform vector. Subtracting the mean in LayerNorm is a projection onto the subspace orthogonal to that vector. Since models don't use that component anyway, subtracting the mean is a redundant step. Llama 1 from February 2023 was the adoption breakthrough. Meta established the recipe: pre-LN plus RMSNorm plus Swiglu plus rope. From that moment, practically every new open-source model, Mistral, Qwen, DeepSeek, Olmo, adopted RMSNorm. The exception is Falcon, which after ablations chose full LayerNorm. Proof that standard choices aren't universally better. RMSNorm simplified normalization. The question of position remains. 2 centimeters in the architecture is the difference between $1 million model that trains and one that diverges. 2 centimeters that change everything. The original transformer architecture from 2017 used post-LN. That famous paper, Attention is all you need. Normalization after adding the residual. It looks logical. Perform the transformation, add the residual, normalize the result. The problem surfaces in backpropagation. The Jacobian of LayerNorm gates the entire gradient flow. The gradient vanishes in early layers. Post-LN requires a long learning rate warm-up and is unstable in deep networks. GPT-2 in 2019 introduced pre-LN, normalization before the sublayer. It looks like a minor change. It's fundamental. The residual pathway stays clean. The one component in the Jacobian provides a direct gradient path. Pre-LN eliminates the need for warm-up. Convergence is up to 40% faster. Pre-LN has its cost. About half the layers in deep pre-LN models behave like identity functions. They can be removed with minimal performance loss. Output variance grows exponentially with depth. Deep layers simply pass the vector forward. Half the skyscraper's floors stand empty. This is the curse of depth. The training log of Meta-OPT, 175 billion parameters, revealed the scale of the problem. The team had to restart training 40 times during the first month. On 1,024 GPUs. Training stability isn't an academic abstraction. It's the daily battle of engineers costing hundreds of thousands of dollars per restart. Gemma, 2 and 3 from Google, and Olmo, 2 from Allen AI, introduced peri-LN. Normalization both before and after the sublayer. A compromise combining pre-LN stability with better variance control. Pre-LN plus RMSNorm is the proven recipe. In 2025, Meta FAIR showed something that challenges a decade of assumptions. Normalization may not be necessary at all. The DT breakthrough, Tanh, is enough. This is the most surprising discovery of 2025 in neural network architecture. Zhu, Chen, He, LeCun, and Liu from Meta FAIR observed something nobody had checked systematically before. LayerNorm in trained transformers produces mappings that resemble Tanh in shape, mostly linear for typical values, suppressing extremes. The conclusion was simple. The entire statistical machinery, computing mean, variance, normalization, scaling, does the same thing as one function, gamma times tan of alpha times x plus beta. The alpha parameter is a learned scalar, initialized at around 0.5 in vision models, with a different value for LLMs. One key new parameter, alongside the standard gamma and beta analogous to LayerNorm, instead of the entire statistical pipeline. The results confirmed the hypothesis across 9 different architectures spanning 4 domains: vision, VIT, convnext, MAE, Dino, diffusion, DIT, language models, Llama, speech, Wave 2Vec20, DNA, Hyena DNA, and Caduceus. DT matches or exceeds normalized counterparts everywhere. Recall what I said about LayerNorm. Santurkar, in 2018, demonstrated that normalization smooths the optimization landscape, not reduces covariate shift. DT closes the loop. S-shaped squashing is enough. A simple curve suppressing extremes. 10 years of statistical normalization, and Tanh was sufficient. The caveat is significant. No production LLM uses DT yet. In December 2025, DERF appeared, a successor using the ERF function, claiming even better results. The field is evolving fast. DT is a warning signal. Obvious architectural assumptions can be wrong. For today, here's the recipe that works. Recipe for a skyscraper that stands. The recommendation for 2026 is clear. First, pre-LN. It preserves the clean gradient highway. For very deep models, peri-LN as a compromise. Second, RMSNorm. Faster, equally effective. The standard since Llama. Third, QK-norm. Normalization of query and key vectors before dot product attention. 2 lines of code that prevent attention logit explosion. Degani and collaborators in 2023 proved this empirically. Without QK-norm, a VIT model with 8 billion parameters diverged with logits above 50,000. Gemma, 2 and 3, Olmo, 2, and Quen, 3, all use QK-norm. 2 extra lines of code protecting against weeks of wasted GPU. Add BF16 instead of FP16. Wider dynamic range, fewer training restarts. Gradient clipping with max norm 1.0 provides a safety net. This recipe is proven by Mistral, Quen, DeepSeek, and Olmo. Be ready for change. DYT and its successors may redefine the fundamentals within the next 2 years. There's one more perspective on residual connections worth mentioning. The residual stream isn't an implementation detail. El-Haj and the team at Anthropic in 2021 made a fundamental reframing. The residual stream is the central communication bus of the transformer. Attention heads and feed-forward layers read from and write to this stream, an office corridor. Employees step out of their rooms, leave nodes on the shared board, and return. The board accumulates knowledge layer by layer. It's the only architectural component of the transformer that has survived a decade unchanged. Let's summarize. Residual connections, the elevator in the skyscraper, are the one sacred element that survived. Normalization evolved through subtraction. BatchNorm, removing batch dependency. LayerNorm, the transformer standard. RMSNorm, removing centering. DYT, removing statistics entirely. Each step removed something deemed essential. Results didn't get worse. Next time you open the architecture of any LLM, every normalization decision will be readable. Subscribe to this channel if you want to understand AI system architecture from first principles. In the comments, share what normalization problems you've encountered in production. See you in the next episode.